Hello everyone, and thanks for watching Edupedia World videos. In this video, we study about the phenomena of interference of light. The first evidence of interference of light was given by one of the most famous experiments in physics, which is called Young's double slit experiment. First, this experiment was done with two small holes, pinholes, but later on, better results were achieved by actually having two slits. So I'll just show you first the diagram of how it works. You take a beam of light, let's say this is a big beam of light, you let it pass through one small slit. So once it passes through one small slit, only a small portion of that light goes through. Actually, the portion goes in many different regions, not just in a straight line. That is due to bending of light on an opening or diffraction, which we'll study in the next video. So anyway, it bends a little bit, and then we have two small slits through which this light passes. We take light from one slit then going into two slits, because what we want is when light enters these two slits, at that point it should have the same phase. And once light enters these two slits, it then just spreads out from these two slits. Both these slits end up becoming secondary sources of waves, just like this one did when this surface was reached by the wavefront. And we capture the final result on the screen, and the result we see is something like this. There will be alternate light and dark bands. What I'm drawing are the dark bands, and there will be light bands. So that happens because of interference of light. So let's say we take this particular point. From this point, light is traveling a certain distance. From this slit, light is traveling a different amount of distance. So these two lights came from the same beam, so had the same initial phase. They travel different amounts of distances, so they have different phases when they meet this point. These points will have two beams of different phases, this will have two beams of different phases. In some places, those phases will be such that they add up to give constructive interference, which will lead to light bands. In other cases, they lead to destructive interference or dark bands. And this phenomena, the phenomena of light and dark bands, can only be explained on the basis of interference, which is a purely wave phenomena. No particles ever show interference. So this particular experiment, which we'll study in detail in a moment, was the major reason the scientific community shifted from believing Newton's version of light being a particle to light being a wave. There are some other reasons as well, which we'll see in a second, but this was the main reason. And whenever we put a light going through one slit, then going through two slits, then captured the result on a screen, it always gave us a band of light and dark fringes. Right? Let's look at this system in a little bit more detail now. So now I'll not draw all the schematic diagrams of it. I'll just draw what is called the top view of the experiment. So these are the two slits. The distance between the slits, let's call it small d. Let's say this is the screen. Let's say this total distance is capital D. Let's say this is the central point. There's no reason to draw this. I'll just mark this out a little bit. This is the central point. Now, when light from these two slits reaches this point, they will have traveled an equal amount of distance. So they will have the same phase, and this point will be constructive interference. Right? So the central point, or what is called the central bright fringe, is the point where both of them have the exact same path, so they have no phase difference at all. Let's consider any other point apart from this. So let's consider light going from this slit and the light going from this slit to a point P. Let's take this distance to be y, and let's take this central angle. Let's take this central angle to be theta. Now we'll make some approximations here. The biggest approximation we'll make is that D is much smaller than capital D. The distance between the slits is much smaller than distance between the slit and the screen. Right? So in that case, we can draw a perpendicular from here. And this is 90 degrees, this is a very big distance. We can assume that this is almost equal to 90 degrees because this angle is very small, and we can assume that this is an isosceles triangle. So if this, let's say, point is A, this point is B, let's say this point is C, then we can assume that AP is approximately equal to CP. Right. In that case, the path difference delta x is equal to BC. If this is theta, and delta x, which is BC, is equal to d sine theta. Right. So from here we get the path difference delta x is equal to d sine theta. Now another approximation we'll use, which also is dependent on the fact that this d is very large compared to either this d or this y as well. Basically, the distance between the screen and the slit is quite large compared to the other dimensions. Then sine theta is quite a small angle, and we can write sine theta approximately as tan theta, which can be written as y by d. Right, we've taken sine theta approximately equal to tan theta. We've seen this sort of stuff many times in simple harmonic motion, which will be equal to y by d. So delta x we get as dy by d. Now let's take a recap for a second and see what actually happens when we actually do have interference. So let's say the first beam has an electric field which is equal to E01 sine kx minus omega t. The other one will have electric field E02 sine k times x plus delta x minus omega t. Right, which can be written as E02 sine kx minus omega t plus phi, where phi is equal to k delta x. Right, so phi is the phase difference between this one and this one, and we already know what the sum of these gives, which we've done that many times. I'll just write the answer right now. The net resultant E will be root of E01 squared plus E02 squared plus 2 E01 E02 cos phi, and the angle between them will be tan delta, whatever the angle is equal to E02 sine phi by E01 plus E02 cos phi. Just as a side note, I hope you see here the beauty of mathematics and why mathematics is so prevalent in physics. The first time we saw this sort of structure was in the addition of two vectors. Right, vectors have nothing to do with what we're doing right now. This is the magnitude of electric field. Right, E01 is the magnitude. E01 is not a vector, it's a scalar. Right, so we did it with vectors. Then we saw the same thing with simple harmonic motion. Then we saw the same thing with light waves. Right, so it's pretty interesting how the similar mathematical equations can have completely different real life meanings. So anyway, when you add these two up, this will ultimately give you, this can also be written, we've seen this as I is equal to I1 plus I2 plus 2 root I1 I2 cos phi. The root is not over the cos. Right, so basically anytime there's a phase difference between these two, it will lead to interference, and that interference can be constructive or destructive depending on what the value of phi is. Right, for a bright fringe we will need this to be constructive interference. In that case we'll need cos phi to be 1. Right, because if cos phi is 1, E is equal to E01 plus E02, and if cos phi is minus 1, then E will be the difference of E01 and E02. Right, so for constructive interference, I'll just rub this now. We won't really need this anymore. Yeah, so this is the main equation, right? So now, if cos phi is equal to 1, that means constructive. That means phi is equal to 2n pi, which is equal to k times delta x, or delta x by lambda times 2 pi. Right, so 2 pi cancel, which means delta x is equal to n lambda. Right, for destructive, cos phi is equal to minus 1, and you can easily check delta x is equal to n plus half of lambda. Right, constructive interference will give rise to bright bands, destructive interference will give rise to dark bands. right? The central point will have a phase difference of 0, which is n lambda, where n is 0. So it will be a central bright fringe, and the intensity generally goes something like this. It decreases as we go out, but this is a bright fringe, then a dark fringe, bright, dark, bright, dark, right? So that's the way it goes. Now let's look at this in terms of delta x. So we know that delta x is equal to dy by capital D, and if that is equal to n lambda constructive, and if delta x is equal to n plus half lambda destructive. That means from here we can see that for constructive, I'll just write bright and dark, that will be more realistic. For bright fringes, delta x is equal to n lambda. That means y is equal to n lambda capital D by small d. And for dark fringes, y is equal to n plus half lambda capital D by small d. Right. So if this was the screen, this was y is equal to 0. Y is equal to 0 will be bright. Then we'll have dark. Then we'll have bright again at y is equal to lambda d by d. Implies y is equal to lambda d by d. Then we'll have dark at 3 by 2 lambda d by d. Then we'll have 2 lambda d by d, where it will be bright again. So what is the distance between two consecutive bright or two consecutive dark fringes? That is called the fringe width, which is symbol is beta, and its formula is lambda capital D by small d. This is the separation between two consecutive bright fringes or two consecutive dark fringes. Just a couple of small mathematical notes. If E01 is equal to E02, that is, generally the intensity is proportional to the width of the slit, and electric field, the square of the electric field is proportional to intensity. So if the width of the slits is the same, the electric field magnitude will be the same. In that case, E is equal to root of E01 squared plus again E01 squared plus 2 E01 E01 cos delta, which you can apply a little bit of mathematics yourself, and you can simplify it as E square. I'll just write it as E0 now, 2 E0 squared 1 plus cos delta, which means I is 2 I0 1 plus cos delta, which can also be written as 4 I0 cos squared delta by 2. So this is another important result, which is only valid when both the electric fields are the same, right, which comes from here. So this is one form of interference we've seen, where we take a slit of light and another slit of light and we make them travel different distances, and that leads to interference. But there can also be other more interesting forms of interference, and the next interference we'll study is the more interesting. And maybe you've seen some incidences of this in real life. When you look at an oil film on a road, let's say a little bit of oil has dropped off some vehicle, and if you look at a film of oil on the road, you can generally see a lot of bright and dark colors. You can see a lot of vivid colors, and that's because an oil film is an ideal substance to have interference. So the next type of interference we'll study is interference from thin films. Before that, we'll revise a concept we've seen in waves earlier, both in sound waves and in waves along a string, and that is what happens when you have light waves or other forms of waves reflected from one medium to another. So we know that if a wave on a string is transferred from a lighter string to a heavier string, then the reflected wave is inverted. And similarly, we know that for sound waves as well, and the similar feature happens in light waves. We'll not give the proof for it, but you've seen the proof for sound waves and waves transmitted on a string, so I hope you just trust me that it is true. What happens is, if light goes from an optically rarer medium to an optically denser medium, in that case there is a phase change of pi. That means it is inverted. Not true if light goes from a denser to a rarer medium. Just like if a wave on a string is going from a heavy string to a light string, the reflected wave is not inverted. In the same way, if it is going from a denser medium, say glass, to a rarer medium, say water or air, then the reflected wave is not inverted, does not have a phase change. But if it is reflected from a rarer to a denser medium, then there indeed is a phase change of pi. Right. So that is the first concept needed. Another concept needed before we interference from thin films is the concept of optical path. So let's say a light wave is traveling and the equation for the electric field is E is equal to E naught sine kx minus omega t. This is the equation, right? And let's say it moves a distance delta x in air. In that case, the new equation will be E is equal to E naught sine k times x plus delta x minus omega t. Right. Let's say this k is the k of air. Right. However, if delta x is moved in water, in that case, E is equal to E naught sine k water times x plus delta x minus omega t. Right. So if we expand the phase of this, it will be k air x plus k air delta x minus omega t, and this will be k water x plus k water delta x minus omega t. So what's the phase difference when delta x is moved in air or water? If it's moved in air, then the phase difference is equal to k air delta x, and for water it is equal to k water delta x, right? Now we know that k is equal to omega by v, where v is the speed of light, and the speed of light is a constant in vacuum, but in different mediums it is different. So we know that the speed of light in, let's say, water will be different from the speed of light in air, right? And the speed of light in water will be smaller, so k will be greater in water. So that means k water is equal to mu water k air, right? K times v is a constant. V is inversely proportional to mu, right? So k is directly proportional to mu. So k water is mu water times k air. What that means is k water times delta x is equal to mu water times k air times delta x. The whole point of this is to tell you that if delta x is moved in a medium of refractive index mu, it is equal to a movement of mu delta x in air. And so mu delta x is called the optical path. All this ultimately arises from the fact that phase difference is in the form of kx, and k changes with mu, right? So if mu is different, k will be different, and then delta x will not just correspond to the phase difference. We have to take care of this optical path mu as well. So whenever light travels a distance delta x in mu, it is the same as traveling a distance mu delta x in air, and we'll use this in our next topic, interference from thin films. Now for our course, we'll only study interference of thin films for normal incidence, because otherwise it gets quite tricky and mathematical. So we'll take almost normal incidence, because with normal incidence the figure won't be quite clear. So let's assume that this is the ground and it has an oil film of thickness d and a refractive index mu, and a light ray falls near normal incidence. It's not exactly normal, but we'll assume it's normal, and it falls here, and a part of it will obviously get reflected back. This is I, let's say this is R. Then a part of it will be refracted inside, and after being refracted, it can either emerge outside, or at this point some of it will again be reflected, and after being reflected the rest of it can go outside or it can actually even get reflected inside and then be transmitted outside. Anytime light goes from one medium to another, some portion of it is reflected, some portion of it is transmitted, and maybe some portion of it is absorbed. So obviously after this it will go on further and further, but we'll not focus on the other ones. We'll just focus on these two. We'll take these two rays and that will create the interference for the reflected rays, and these two rays will create the interference for the transmitted rays. Right? And delta X we will take to be the optical path, not the actual path, because some of it is moved in air and some of it is moved in water. Right? So let's look at these two transmitted waves. What is delta X between these two transmitted waves? Right, up till this point they are the same. Then the first ray moves from here, the second point moves an extra this much distance and moves back. And we are assuming that IR and all the angles are small, it's all near normal incidence. So we'll assume both this and this length to be equal to D. Right. So delta X is equal to 2D is the distance moved by this particular ray. So delta X is the path difference between this ray and this ray. But what is the phase difference? For that we'll need the optical path, and optical path will actually be 2 mu times D, because this distance of 2D is moved in a medium of refractive index mu, so it is equivalent to an optical path of 2 mu D. Right? This is the path difference, or the phase difference will be K times this between these two rays. Also, another point is that there is no factor of pi, because here there is a reflection. Actually, there is a factor of pi for this one. This reflection is going from a rarer to a denser medium. Right? So here there will be a phase change of pi. And after this, at this reflection, there will be no phase change of pi because it is going from a denser to a rarer medium. So delta, the phase difference for the reflected rays, is equal to 2 pi by lambda, which is K, multiplied by 2 mu D, but there will also be a factor of pi. And the factor of pi is because when the ray is deflected from here to here, then it is reflected from a rarer to a denser medium. It's almost like wave is going from a light rope to a heavy rope. The reflected one will be inverted. Let's look at what will be true for the transmitted waves. These two are the transmitted waves. The only difference suffered is these two. So again the optical path will be 2 mu D. However, both this reflection and this reflection occur from denser to rarer mediums. So they will not have any phase difference of pi. So delta transmission will simply be 2 pi by lambda times 2 mu D. Right? So let's now analyze this mathematically. Delta for reflection or reflected rays is equal to 2 mu D times 2 pi by lambda plus pi. Right? Now this is the net phase difference, and this will lead to constructive interference if this is equal to 2 pi, 2n pi, or destructive interference if this is equal to 2n plus 1 pi. If we take this is equal to 2n pi, in that case what we'll get is 2 mu D times 2 pi by lambda is equal to 2n minus 1 times pi, or we'll get 2 mu D is equal to pi cancels 2n minus 1 lambda by 2. Right? So for there to be a bright fringe in the reflected rays, we need 2 mu D is equal to 2n minus 1 lambda by 2. For there to be a dark fringe in the reflected rays, you can do it yourself. 2 mu D is equal to 2n lambda by 2, or mu D is equal to n lambda. 2 mu D is equal to n lambda. Right. So this is for bright and this is for dark fringes. And it's exactly the opposite for transmitted ones, which also it makes sense, because if for a particular value of 2 mu D you have constructive interference for both reflected and transmitted, then you have extra energy. And if you have destructive interference for both reflected and transmitted rays, then you have actually loss of energy. That does not happen, and actually this bright condition, you can check, it is dark. It is dark for transmitted rays. And this condition 2 mu D is equal to n lambda, it is bright for transmitted rays. right? So 2 mu d is equal to 2n minus half lambda by 2. That means it will be constructive interference for the reflected rays. So the reflected rays will be bright and the transmitted rays will have destructive interference, so they will be dark. If 2 mu d is equal to n lambda, then the reflected waves will destructively interfere and you will not see any light on the other end, but the transmitted waves will have bright and all the rays will be transmitted because it will be constructive interference. Right. Now there are some other cases which can actually be treated like a YDAC case. The simple case which is generally studied is called the Fresnel biprism. We'll not go into the mathematics of it because that's not in your course, but what happens is we have a single point source and we'll take a prism with a very wide vertex angle and two very small base angles. And if we put a light source in front of a prism, even then we observe bright and dark bands. And the reason we then observe bright and dark bands is because some light will go here and some other light will go like this. And let's say there's another light which goes here and there's another light which goes here. Then when you produce these two backwards, it seems as though this light is coming from two different sources. Right. So when you have one single source in front of a prism, then the rays meet in such a way that it would seem as though there are two different sources, and two different sources we know for different path differences will give interference pattern. So not only do two different slits give an interference pattern, but even when one single slit is placed in front of a prism, it gives us an interference pattern. This completes interference. The next wave phenomena which we'll study in the next video are diffraction and polarization. And then we'll move on to geometrical optics, where we'll see the standard mirror and lens formulas which you've already seen. Thank you.